Hello everyone. Today we will study vector functions. First of all, let me introduce what is a vector function. A vector function in R3 is the function R from real number R to R3. Which assigns each real number to a vector in R3. A vector function in R3 is the function R from real number R to R3, which assigns each real number to a vector in R3. So, a vector function in R3 looks like this. R of t, it has three components: x of t, y of t, and z of t. Because a vector in R3 has three components, so R of t, it assigns a real number t to a vector x, y, z. This function R assigns a real number t to a vector s, y, z. Next, let me show you an example. Let R of t be 1 minus 3t, 2 plus 2t, and 3 plus t. Sketch its graph. Sketch its graph. This vector function has three components: x, y, z. X equal to 1 minus 3t, y equal to 2 minus 2t, z equal to 3 plus t. If we consider these equations as parametric equations, this s, y, z represent a line. This s, y, z represent a line. In order to graph a line, we need to plot 2 points. Once we plot 2 points, by connecting 2 points, we can make a line. Once we know 2 points, by connecting 2 points, we can make a line. So let's find 2 points. Let's find 2 points on the line. If I plug in 0 to the vector function, I have 1, 2, 3. If I plug in 0 to the vector function, I get point 1, 2, 3. I get vector 1, 2, 3. If I plug in 1 to the vector function, I get negative 2, 4, and 4. So when I plug in 0, I get a vector 1, 2, 3. When I plug in 1, I get a vector negative 2, 4, 4. Here, we consider these two vectors as position vectors. They represent points. We consider these two vectors, they are position vectors. For position vector, we can consider they are points. For position vectors, we can consider they are points. So let's plot point 1, 2, 3 and negative 2, 4, 4. Then by connecting 2 points, we can make a line. Let's plot the first point first. 1, 2, 3. S is 1, Y is 2. Let's point 1, 2 in the SY plane. Then Z coordinate is 3. I shift this point up by 3 units. shift this point up by 3 units. Somewhere here. This is point 1, 2, 3. The second point, -2 and -2, 4, 4. Let's plot the point in the xy plane first. X is -2, y is 4. That's -2 and 4 in the xy plane. Then since z coordinate is 4, I shift this point up by 4 units. Shift this point up by 4 units. That's the point -2, 4, 4. Then by connecting 2 points, we can make a line. By connecting 2 points, we can make a line. And here we know that at this point 1, 2, 3, t is 0. At this point, -2, 4, 4, t is 1. So, as t increases, that's the direction of the line. T is 0, t is 1. As t increases, that's the direction of the line. So, this is the graph. This is the graph of this vector function. This is the graph of this vector function. And that's the direction as t increases. Next example. Let the vector function r of t be cosine of t, sine of t, and t. Sketch its graph. In this vector function, let's observe the component first. X component is cosine t, y component is sine t, z component is t. How do we sketch the graph? Let's observe the x and y component first. If we only look at x and y component, treat x and y as a parametric equations. So if I square both sides, x squared equal to cosine square of t, y squared equal to sine square of t. Then x squared plus y squared is 1. So that means if I treat x and y as parametric equations, the graph for x and y for this parametric equation is a circle in the xy plane. If we treat x and y as parametric equations, the graph is a circle in the xy plane. It's a circle center and origin with radius 1. If we treat x and y as parametric equations, their graph is a circle in the xy plane, center and origin with radius 1. Now what's the direction? What's the direction of the curve as t increases? What's the direction of the curve as t increases? Let's plug in some numbers. If I plug in 0 for t, cosine 0 is 1, sine 0 is 0. We get point 1, 0, which is here. When t is 0, the point is here. Cosine 0 is 1, sine 0 is 0. What if I plug in pi over 2? If I plug in pi over 2, cosine pi over 2 is 0, sine pi over 2 is 1. So we get point 0, 1. The point is here. So that's the direction. That's the direction of the curve as t increases. That's the direction of the curve as t increases. Now, let's consider the z component. If we involve the z component, we can see that z equal to t. So as t increases, z increases at the same time. So as t increases, the curve will follow the same path, but it's moving upward. It's moving upward around the z-axis. It's moving upward as t increases. So let me show you the 3D graph. The 3D graph looks like this. Since the curve is moving around a circle, and it's moving upward, the curve looks like a spring. It looks like a spring. When t is 0, the point is here. Then as t increases, the curve will move upward. From the same path, but it's moving upward. That's the direction of the curve as t increases. And also, t could be negative. T could be negative. So that's the graph of this vector function. That's the graph of the vector function. The curve is moving around the circle in the xy plane. But as t increases, the curve is moving upward around the z-axis. That's the graph of this vector function. So based on these two examples, we can see that the graph of a vector function is always a curve. Since the previous example, the graph of a vector function is a curve. We consider straight line is a special curve. So the graph of a vector function is a curve. Keep this idea in mind. In general, the graph of a vector function is a curve. The graph of a vector function is a curve. And we can consider the vector function as a particle moving along the path. We can consider the vector function as a particle. Say trace on the curve. We can consider the vector function as a particle traced on the curve as t varies. So as t increases, the particle is traced along the curve. Let's say here, as t increases, we can consider the vector function as a particle traced on the curve as t increases. Next, let me show you how to use a vector function to represent a curve. Find a vector function which represents the straight line passing through points -4, 2, 3, and 2, 1, 0. Find a vector function which represents a straight line passing through these 2 points. We know that equation of a line is always a vector function. Equation of a line is always a vector function. Equation of a line is r of t equal to r0 plus tv. Equation of a line is always a vector function. Here, r0 is a point on the line. V is the directional vector of the line. For r0, you can use either point. Let me use the first point for r0. So when I plug in into the vector function, I need to consider r0 as a position function. So consider this point as a position vector. You need to consider r0 as a position vector. Consider this point as a vector when we plug into the equation. When we plug in r0, we must consider this point as a position vector, write it as a vector. V is the directional vector of this line. V is the directional vector of the line. Since we know 2 points on the line, join these 2 points, we can find a vector. Join these 2 points, we can find a vector. Use head minus tail. Use head minus tail, we can find a vector. So consider this is head, this is tail. Head minus tail. 2 minus -4 is 6. 1 minus 2 is -1. 0 minus 3 is -3. That's the directional vector. That's a point on the line. Then we can plug in, find a vector function. And this vector function represents a line passing through these 2 points. R0 plus TV. V is 6, -1, -3. Distribute t, we get 6t minus t minus 3t. Add the vectors. We have -4 plus 6t, 2 minus t, 3 minus 3t. This is a vector function. This is the vector function which represents a line passing through these 2 points. Next example. Find a vector function which represents the intersection of a cylinder x squared plus y squared equal to 4. And the plane y plus z equal to 4. Let me first of all show you the picture. How the intersection looks like. How the intersection of a cylinder and a plane looks like. Let me show you the picture first. A cylinder looks like this. That's a graph of a cylinder. A plane. How does a plane looks like? A plane y plus z equal to 4 looks like this. That's a plane y plus z equal to 4. The intersection looks like this. That's a plane, that's a cylinder. That's the intersection. The intersection here looks like ellipse. The intersection looks like ellipse. We try to find a vector function to represent this ellipse. What can we do here? Let's observe the cylinder. S squared plus y squared equal to 4. If we consider s and y as parametric equations, can we find a parametric equation for s and y? If we consider s and y as a parametric equations, can we find a parametric equations for y, for s and y? When we have s squared, y squared, think of sine squared, cosine squared. If I divide both sides by 2, I have s squared over 4 plus y squared over 4 equal to 1. S squared over 4 can be rewritten as x over 2 squared. Y squared over 4 can be rewritten as y over 2 squared equal to 1. We know that cosine squared plus sine squared equal to 1. So I can let x squared over 2 equal to cosine of t, y over 2 equal to sine of t. Then I can solve the equation for s and y. S equal to 2 cosine t, y equal to 2 sine t. This parametric equation satisfies all points on the cylinder. This parametric equation satisfies all points on the cylinder. And we know that in the intersection, it must satisfy all points in the cylinder and all points, it must satisfy both equations, the equation of the cylinder and the equation of the plane. For the point on the intersection here, for the point on the intersection, the point must satisfy both equations. For the point on the intersection, the points must satisfy both equations. So we can plug in y here and solve for z. We have y plus z equal to 4. In the plane, the equation is y plus z equal to 4. If I plug in y, it's 2 sine t. I can solve this equation for z. Here, z equal to 4 minus 2 sine t. So SYZ, this SYZ satisfies both equations. If I solve z like this, SYZ satisfies both equations. So it represents all points on this ellipse, which is their intersection. And here, SYZ, they are all functions of t. I can put them together and form a vector function. Write R of t as x, y, z together. Cosine of t, 2 cosine of t, 2 sine of t, 4 minus 2 sine t. That's the x component, y component, z component, and they satisfy both equations. So this vector function represents this ellipse, which is the intersection of this cylinder and the plane. Next, let me show you limits of functions. Let R of t equal to x of t, y of t, z of t be a vector function. the limit of R of t as t approach to a is defined as the limit as t approach to a R of t equal to the limit t approach to a x of t, the limit t approach to a y of t, and the limit t approach to a g of t. So for limit of a vector function, take a limit for each component individually. For limit of a vector function, take a limit for each component individually. Next, let's look at a simple example. Then the vector function R of t equal to t cosine t squared minus t over e to the power t minus 1 ln of t minus 1 squared. Find the limit as t approach to 0 R of t. So let's take limit. Limit as t approach to 0. For the vector function, we take limit for each component individually. So for the first component, take a limit as t approach to 0, t cosine t. For the second component, take a limit as t approach to 0, t squared minus t over e to the power t minus 1. For the third component, take a limit as t approach to 0, t squared minus 1 squared. Take a limit for each component individually. Take a limit for the first component, t approach to 0, t times cosine t. If I plug in 0, I get 0 times cosine 0. Cosine 0 is 1. I get 0 times 1. 0 times 1 is 0. So the limit for the first component is 0. Next, take a limit for the second component. Limit as t approach to 0, t squared minus t over e to the power t minus 1. If I take a limit, I plug in 0 for t. Numerator is 0. Denominator e to the power 0 is 1. 1 minus 1 is also 0. When we have 0 over 0, we can apply L'Hopital's rule. If we apply L'Hopital's rule here, the numerator is 2t minus 1. Denominator is e to the power t. When t goes to 0, numerator is negative 1. Denominator e raised to power 0 is 1. Negative 1 over 1 is negative 1. So the limit for the second component is negative 1. Next, take a limit for the third component. As t approach to 0, ln of t minus 1 squared. Limit ln of t minus 1 squared. If I plug in 0 for t, 0 minus 1 is 1. 1 squared is 1. ln of 1 is 0. So the third component is 0. Therefore the answer, limit as t approach to 0, the limit is 0, negative 1, 0. The limit is a vector, 0, negative 1, 0. Next, let me introduce the derivatives of vector functions. Let R of t be a vector function with components x of t, y of t, g of t. So let r of t be a vector function. Then its derivative r prime of t can be expressed as r prime of t equal to x prime of t, comma y prime of t, comma z prime of t, which means we take derivative for each component individually. Next, let's look at a simple example here. Let r of t be sine t squared e to the power of 2t, t times ln of t. Find its derivative. Find r prime of t. What can we do? We take derivative for each component individually. So for r prime of t, we take derivative for each component individually. For the first function, use chain rule here. We have cosine of t squared times 2t. For the second component, use another chain rule. E raised to 2t times 2. For the third component, use product rule here. Derivative of the first times the second plus the first times derivative of the second. They can be rewrite as 2t times cosine of t squared. Two times e to the power of 2t, ln of t plus 1. This is r prime of t. Here we can see that r prime of t is the derivative of a vector function, and r prime of t itself is also a vector function. What does this vector represent? Let me show you a rough graph first. We know that the graph of a vector function r of t is a curve. In general, it's a curve. Suppose that's a graph of r of t. Assume that's the direction of the curve as t increases. Let P be a point on the curve. And suppose P is the point R of T0. Suppose P is the point R of T0. Then R prime of T0, the derivative at point P, R prime of T0 represents the directional vector of the tangent line at point P. R prime of T0 represents the directional vector of the tangent line at point P. R prime of T0 represents the directional vector of the tangent line at point P. So keep this idea in mind. Note, let R of t be a vector function and let P with P equal to R of T0 be a point on the graph of the vector function. On the graph of R of t. Then the derivative R prime of T0 First of all, this is a vector. It represents the directional vector of the tangent line. At point P. R prime of T0 represents the directional vector of the tangent line at point P. So R prime of T, in general, R prime of T is also called the tangent vector. It's also called the tangent vector of R of T, of the vector function R of T. Because R prime of T0 represents the directional vector of the tangent line at point P. So in general, R prime of T is called the tangent vector of R of T. R prime of T in general is called the tangent vector of R of T. Since it represents the directional vector of the tangent line, it's called the tangent vector of R of T. Also, if we consider the vector function R of T as a particle traced on a curve, then at point P, R prime of T0 shows where and how fast this particle is moving. And this arrow shows the direction. This arrow shows the direction. If the arrow is long, that means this particle is moving faster. If this arrow is short, that means this particle is moving slower. So at point P, R prime of T0 shows where and how fast this particle is moving. So keep this idea in mind. If we consider the vector function R of T as a particle traced on a curve, then at point P, where P is R of T0, then at point P, R prime of T0 shows where and how fast the particle is moving. Since R prime of T0 shows where and how fast the particle is moving, it's called the velocity. It represents the velocity of the particle. So R prime of T represents the velocity of the particle. R prime of T represents the velocity of the particle. On the curve. Hence, R prime of T is called a velocity function. Hence, R prime of T is called a velocity function. So if we consider R of T as a particle move on a curve, R prime of T is called a velocity function. Next, let me show you some differentiation rules. let u of t and v of t be vector functions. And let k be a constant. Let k be a real number. First rule. The derivative of u of t plus v of t. For the derivative of u of t and v of t, we take derivative for each function individually, equal to u prime of t plus v prime of t. This is called the sum rule. Derivative of u of t plus v of t is u prime of t plus v prime of t. This is called the sum rule. Next, the derivative of a constant k times u of t. The derivative of a constant k times u of t. That's k times u prime of t. That's k times u prime of t. This is called a constant multiple rule. This is called a constant multiple rule. Next, the derivative of f of t times u of t. Here, f is a scalar function. F is a scalar function. Let f of t be a scalar function. And k is a real number. Here, f is a scalar function. When we have a scalar function times a vector function, we use product rule here. When we use scalar function times vector function, we use product rule here. The product rule is derivative of the first times the second plus the first times derivative of the second. When we have a scalar function times a vector function, we use product rule. When we have a scalar function times a vector function, we use product rule. Derivative of the first times the second plus the first times derivative of the second. Next, when we have a function, vector function u, dot a vector function of v. When we take derivative for dot product, we also use product rule. It's the derivative of the first dot the second plus the first dot derivative of the second. So when we take derivative for dot product, apply product rule. Derivative of the first times the second plus the first times derivative of the second. When we take derivative for dot product, use product rule. Next, when we take derivative for cross product, u of t cross v of t. When we take derivative for cross product, u of t cross v of t, we also use product rule. U prime of t cross v of t plus u of t cross v prime of t. Derivative of the first times the second plus the first times derivative of the second. When we take derivative for cross product, we also use product rule. Now, let me remind you one thing. For cross product, the order matters. For cross product order matters, we must write it exactly in this order. For cross product order matters, we must write it exactly in this order. For dot product, order doesn't matter. If you write the second part first, it's okay. If you write u of t times u of v prime of t, if you write v of t in the front, u prime of t in the back, that's okay. For dot product, order doesn't matter. But for cross product, order matters. We must put it exactly in this order. For cross product, order matters. We must exactly put it in this order. And for 3, 4, 5, be very careful. This is regular multiplication, a scalar times a vector. This is dot product. This is cross product. We all use product rules for this 3 expression. Use product rules for scalar times a vector dot a vector, and a cross product, a vector cross a vector. Use product rules for 3, 4, 5 for these 3 formulas. And only for cross product, the order matters. For cross product, order matters. We must put it exactly in this order. Next one is called a chain rule. Derivative of u of f of t. This is called chain rule. Derivative of u of f of t. When we have a function inside another function, we use chain rule. The chain rule says, do an outside function first. Take derivative for u first. Keep the inside the same. Times f prime of t times the derivative of an inside function. This is called chain rule. When we have a function inside another function, we use chain rule. Do an outside function first. Keep the inside function the same. Times the derivative of an inside function. This is called chain rule. Those are the differentiation rules. Those are the differentiation rules for vector functions. Next, let me show you some examples. Let r of t be sine t e to the power t ln of t, and let f of t equal to t to the power of 3. Find the derivative of f of t times r of t and the derivative of r of f of t. So first one, when we take derivative for scalar function times vector function, we can use product rule. When we take derivative for scalar function times vector function, we can use product rule, which is derivative of the first times the second plus the first times derivative of the second. So for f prime of t, we take derivative. For f prime of t, take derivative for function f. Take derivative for function f, we have 3t squared. R of t, keep the vector function exactly the same. Sine of t e to the power t ln of t plus f of t is t cubed times r prime of t. If I take derivative for function r, take derivative for each component individually. First component, derivative of sine is cosine. Derivative of e stays the same. Derivative of ln of t is 1 over t. Then simplify, we distribute 3t squared. We have 3t squared times sine t. 3t squared times e to the power t. 3t squared times ln of t. If we distribute t cubed, we have t cubed cosine t. T cubed e to the power t. And t cubed times 1 over t squared is t squared. Then we can add these two vectors together. and add these two vectors together. First component is 3t squared times sine t plus t cubed times cosine t. That's the first component. The second component is 3t squared e to the power t plus t cubed e to the power t. That's the second component. The third component, we have 3t squared ln of t plus t squared. That's the third component. Now how do we do product? How do we do chain rule here? When we take derivative for r of f of t, we use chain rule here. Do the outside function first. R prime of f of t times f prime of t. R prime of f of t. We first of all take derivative for r first. R prime of t is cosine t times et times 1 over t. That's r prime of t. Then for r prime of f of t, we plug in f of t into the function. We have cosine of f of t is t cubed e of t cubed. We plug in f of t for each t. 1 over t cubed. For r prime f of t, we plug in f of t for each t. And f of t is t cubed. This is cosine t cubed e to the power of t cubed 1 over t to the power 3 times f prime of t. F prime of t is 3t squared. When we have a scalar times a vector, we distribute a scalar into each component. When we have a scalar times a vector, we multiply the scalar to each component in the vector. So we have 3t squared times cosine t cubed. 3t squared times e to the power of t cubed. And 3t squared times 1 over t cubed is 3 over t. Let's chain rule. Now let me say this. If we don't use product rule and we don't use chain rule, we should get exactly the same answer when we take derivative. If we don't use product rule and we don't use chain rule, we should get exactly the same answer. Let me show you how to take derivative without using product rule and chain rule. If I take derivative without using product rule and chain rule, we should get exactly the same answer. If I don't use product rule, I first of all multiply function f and rt. I first of all multiply function f into function r. Function f is t cubed. R of t is sine t e to the power t ln of t. Then when we have a scalar times a vector, we distribute the scalar to each component. If I distribute, I have t cubed times sine t cubed times e to the power t cubed times ln of t. Then when we take derivative for a vector function, take derivative for each component individually. When we take derivative for each component, take We won't take derivative for vector function. Take derivative for each component individually. Then take derivative for each component. T cubed times sine t, here we use product rule. Derivative of the first times the second plus the first times derivative of the second. Here do product rule. Derivative of the first times the second plus the first times derivative of the second. That's the second component. For the third component, we have derivative of the first times the second plus the first times derivative of the second. If I simplify, I have 3t squared sine t plus t cubed cosine t, 3t cubed e of t plus t cubed e of t, 3t squared ln of t plus t squared, which is exactly the same as what we have here. If we don't use product rule for vector functions, we get exactly the same answer. If we don't use product rule for vector functions, we get exactly the same answer. And similarly, if we don't use chain rule here, we simplify what's in the bracket first, and then take derivative, we should get exactly the same answer. Let me show you here. If we simplify what's in the bracket first, then take derivative, answer should be exactly the same. So derivative of r of f of t. If we simplify what's in the bracket first, we have r of f of t r of f of t means we plug in function f, plug function f into function r, plug function f into function r, plug in f of t for each t. We have sine of ft, f of t is t cubed, e to the power of f of t is t cubed, ln of f of t, ln of ft is t cubed. So we plug in f of t for each t, then take derivative. When we take derivative for vector function, we take derivative for each component individually. Derivative of sine t cubed, that's the first component. Derivative of e to the power t to the power 3. Derivative of ln of t cubed. Ln of t cubed, we can bring power 3 to the front, make it a little easier. We can bring power 3 to the front. For ln of t cubed, we can bring power 3 to the front. But there's 3 ln of t. That'll be a little easier. Then take derivative for each component. We have cosine t cubed times 3t squared e to the power of t cubed times 3t squared, 3 times 1 over t. Then this vector function can be rewrite as 3t squared cosine of t cubed, 3t squared times e to the power of t cubed. And 3 times 1 over t can be rewrite as 3 over t. That's the derivative of this function without using chain rule for vector functions. That's the derivative for this vector function without using chain rule for the vector functions. We get exactly the same thing. So for all these formulas here, if we simplify what's in the bracket first, then take derivative, which will get exactly the same answer as we use the formula. If we simplify what's in the bracket first, then take derivative, which will get exactly the same thing as we use the formula. So sometimes, in general, using the formula can make the problem easier. In general, using this formula, using this differentiation rule, it can make the problem easier. Next, let me show you a theorem. Let R of t be a vector function. If the derivative of the vector function is always a constant, then R of t is perpendicular to R prime of t for all t. If the magnitude of a vector function is always a constant, then R of t is perpendicular to R prime of t for all t. Let's prove it. So let the magnitude of R of t equal to a constant c. Then if I square both sides, magnitude of R of t square equal to c square. Then we know for dot product, there's a property says, A dot A, for any vector A dot A, that equal to the magnitude of vector A square. For dot product, next property says, for any vector A dot A is the same as the magnitude of vector A square. So this is a vector R prime of t. R of t is a vector function. When we take magnitude of this vector square, I can write it as the dot product of this vector. So that's the same as R of t dot R of t by this property. Magnitude of a vector square is the vector dot itself. The magnitude of a vector square is the vector dot itself. Next, if I take derivative on both sides, I have R of t dot R of t equal to the derivative of c squared. Take derivative on both sides with respect to t. Then for dot product here, we can use product rule. Derivative of the first dot the second plus the first dot the derivative of the second. That's product rule. Derivative of the first times the second plus the first times derivative of the second. This is dot product. Then derivative of c squared. C is a constant. Derivative of constant is 0. Then for dot product, we know that A dot B, for any vector A dot B is the same as B dot A. And that's the commutative law for dot product. That's a commutative law for dot product. If I switch two vectors, the dot product stays the same. So R prime of t dot R of t is the same as R of t dot R prime of t by commutative law. That's the same as R of t dot R prime of t. Now they are exactly the same. If I combine like terms, I get twice R of t. If I combine like terms, I get twice R of t. Dot R prime of t equal to 0. Then I can divide both sides by 2. So R of t dot R prime of t equal to 0. If for any two vector, if the dot product is 0, they must be perpendicular. For any two vectors, if their dot product is 0, they must be perpendicular. So R of t is perpendicular to R prime of t for all t. That's a proof of the theorem. So for this theorem, keep in mind that for any vector function, if its magnitude is always a constant, then this vector function is always perpendicular to its derivative. So keep this idea in mind. For any vector function, if its magnitude is always a constant, then this vector function is always perpendicular to its derivative. Keep this idea in mind. Next, let me show you the integrals of vector functions. Let R of t equal to x of t, y of t, z of t be a vector function. Then the integrals integral R of t dt and the integral R of t dt. T varies from a to b. This is called an indefinite integral, and this is called a definite integral. This is called an indefinite integral, and this is called a definite integral. These two integrals can be expressed as these two integrals can be expressed as the indefinite integral R of t dt. That's integral x of t dt. That's the first component. Integral y of t dt. That's the second component. Integral z of t dt. That's the third component. So for vector functions, when we take integral for each component individually. And same thing for definite integral, it's the same thing. T varies from a to b. R of t dt, that's integral from a to b, x of t dt. Integral y of t dt, t varies from a to b. Integral z of t dt, t varies from a to b. So that's how we take integrals for vector functions. That's how we take integrals for vector functions. When we take integral for vector functions, take integral for each component individually. When we take integral for a vector function, take integral for each component individually. Next, let's look at an example about integrals. Let the vector function R of t be sine t, 2, and secant squared t, Find the indefinite integral r of t dt and the definite integral r of t dt. T is from pi over 6 to pi over 3. Let's solve the indefinite integral first. Integral of r of t dt. Here r of t is a vector function. When we take integral for a vector function, we take integral for each component individually. That's integral of sine of t dt, comma, integral of 2 dt, comma, integral of secant square t dt. Take integral for each component individually. Then take antiderivative for sine t. We have antiderivative of sine is negative cosine. We have negative cosine t. When we take antiderivative, we must add a constant called c1 here. Take antiderivative for number 2 with respect to t. We get 2t. When we take antiderivative, we need to add constant called c2 here. Take antiderivative for secant square t. When we take antiderivative for secant square t, we have tension t. And when we take antiderivative, we need to add constant called c3 here. That's an indefinite integral. Next, let's take this definite integral. From pi over 6, t is from pi over 6 to pi over 3. R of t dt. Same thing, when we take integral for a vector function, take integral for each component individually. When we take integral for a vector function, take integral for each component individually. First component, sine t dt. T is from pi over 6 to pi over 3. Second component, integral from pi over 6 to pi over 3, 2 dt. Third component, integral t is from pi over 6 to pi over 3, secant square t dt. Then solve each integral individually. When we solve for the first integral, take antiderivative for sine. Antiderivative of sine is negative cosine t. Since this is definite integral, we don't add constant c. Since this is a definite integral, we don't add constant c. Evaluate from pi over 6 to pi over 3. Next, take antiderivative of 2 with respect to t. We get 2t. Evaluate from pi over 6 to pi over 3. Next, take antiderivative for secant square t with respect to t. We get tension of t. Evaluate from pi over 6 to pi over 3. Solve each component individually. For the first component, if I plug in pi over 3, cosine pi over 3 is half. Cosine pi over 6 is radical 3 over 2. If I plug in pi over 3 for t, I get 2 times pi over 3. If I plug in pi over 6 for t, I get pi over 6. Let's leave number 2 by itself. Plug in pi over 3 for t, plug in pi over 6 for t, leave number 2 by itself. If I plug in pi over 3 for t, tension pi over 3 is square root of 3. If I plug in pi over 6 for t, tension pi over 6 is square root of 3 over 3. Then, if I simplify the first component, they have the same denominator. If I distribute negative sign, square root of 3 become positive. Number 1 become negative. Pi over 3 minus pi over 6 is pi over 6. Pi over 6 times 2 is pi over 3. That's the second component. Square root of 3 minus square root of 3 over 3. Put square root of 3 over 1. Then find common denominator, which is 3. Then multiply top and bottom by 3. You get 3 square root of 3 over 3. 3 square root of 3 minus square root of 3 is 2 square root of 3 over 3. That's an answer to this definite integral. So keep in mind that when we take definite integral for a vector function, the answer is always a vector. When we take definite integral for a vector function, the answer is always a vector. But when we take an indefinite integral for a vector function, the answer is another vector function. When we take an indefinite integral for a vector function, the answer is always another vector function. Next, let me show you motion in space. Let R of t equal to x of t, y of t, z of t be a vector function. If we consider R of t as the displacement of a particle in R3, then its velocity, acceleration, and speed are defined as v of t, velocity v of t, is x prime of t, y prime of t, z prime of t, which is the first derivative. V prime of t is the first derivative of R of t. That's called velocity. Acceleration, A of t, is the second derivative. A of t is the second derivative. That's x double prime of t, y double prime of t, z double prime of t. The acceleration is the second derivative of the velocity of the vector function. The acceleration is the second derivative of the vector function. Now, the speed of the particle is defined as the magnitude of the velocity function. The speed is defined as the magnitude of the velocity function, which is square root of dx over dt squared plus dy over dt squared plus dz over dt squared. That's the speed of the particle. Next, let's look at an example here. Let the vector function R of t equal to t squared, t cubed, 3t represent the displacement of a particle in R3. Find its velocity, acceleration, and speed at point 4a6. So let's compute its velocity and acceleration first. Velocity is the derivative of the vector function, which is 2t, 3t squared, and 3. The acceleration is the second derivative of the vector function, which is 2, 6t, and 0. How about the speed? The speed is the magnitude of the velocity. The speed is the magnitude of the velocity, which is square root of 2t squared plus 3t squared squared plus 3 squared. If we simplify, we get square root of 4t squared plus 9t to the power 4 plus 9. That's the speed. Next, we need to find actual value. So we need to plug in t value for an actual value for this velocity, acceleration, and speed at this point 4a6. So let's find t first. Since r of t, the vector function r of t represents the displacement, so the s component must be 4, the y component must be 8, and the z component must be 6. So we set t squared equal to 4, t to the power 3 equal to 8, 3t equal to 6. Solve these equations for t. We take their common solution. If we solve the first equation for t could be either positive 2 or negative 2. If we solve the second equation for t must be 2. If we solve the third equation for t is also 2. So the common solution is t equal to 2. We plug in 2 into the velocity, acceleration, and speed functions. So when t equal to 2, the velocity is 2 times 2, which is 4. 3 times 2 squared is 12. 3 by itself is 3. The acceleration, when t is 2, for the acceleration, we plug in 2 for t. Number 2 is a constant, stays the same. 6 times 2, if I plug in 2 here, 6 times 2 is 12. And 0 is a constant, stays the same. For the speed, we plug in 2 here. 2 squared is 4. 4 times 4 is 16. 2 to the power 4 is 16. 16 times 9 is 144. 9 stays the same. 16 plus 144 is 160. 160 plus 9 is 169. Square root of 169 is 13. So that's the velocity. Velocity, acceleration, they are vectors. Speed is a constant. Speed means how fast the particle is moving. That is a constant. Vector and acceleration, they are both vectors. Velocity and acceleration, they are both vectors. Speed is a constant. Speed shows how fast the particle is moving. Speed is a number. Velocity and acceleration, they are vectors. Next example. An object starts from rest. Start from rest means it's not moving. And the point one, 2, 0. And move with acceleration. Move with acceleration a of t. Equal to 0, 60, and 2. Find the location of the object. When t equal to 3. We know that vector function r of t represents displacement. V of t represents velocity. A of t represents acceleration. From displacement to velocity, we take derivative. And from velocity to acceleration, we take another derivative. If we try to go backward, from acceleration to velocity, we take antiderivative. If we want to go from velocity to displacement, we take another antiderivative. So from displacement to velocity, we take derivative. From velocity to acceleration, we take another derivative. If we try to go backward, from acceleration to velocity, we take antiderivative. From velocity to displacement, we take another antiderivative. In this problem, we are looking for the location of an object. That means we are looking for the displacement of an object. And all we know is the acceleration. So if we know the acceleration, we try to find the displacement, we must take antiderivative twice. If we know the acceleration and we try to find the displacement, we must take antiderivative twice. So start from acceleration, take antiderivative twice, find the displacement, then based on displacement, we find the location of an object when t is 3. So let's write down the given information first. We know that an object starts from rest. That means initially when time is 0, this object is not moving, there's no velocity on the object. So when time is 0, the velocity is a 0 vector. That's what an object starts from rest means. An object starts at a point 1, 2, 0. That means initially when time is 0, the displacement when time is 0, when t is 0, the displacement is 1, 2, 0. That's the displacement when time is 0. That's what's given. That's the initial velocity, and that's the initial displacement. That's what's given. And what we also know is the acceleration. What we also know is an acceleration function. Acceleration function is 0, 6t, and 2. Based on the acceleration function, we try to find the displacement. That means we need to take antiderivative twice. Let's first of all take antiderivative to find the velocity. If I take an antiderivative for the acceleration function, I can find the velocity. Antiderivative of 0 is a constant. It's called C1. Antiderivative of 0 is a constant. Let's call C1 here. Antiderivative of 6t is 3t squared. Antiderivative of 6t is 3t squared. And when we take antiderivative, we need to add constant. Let's call C2. When we take antiderivative, always add constant. Let's call C2 here for the second component. For the third component, when I take antiderivative for 2, I get 2t. And when I take antiderivative, I add constant. Let's call 3 here, C3 here. That's the velocity. Now we need to find C1, C2, C3. We need to find C1, C2, C3. We know that V0 is 0, 0, 0. If I plug in 0 here, what do we get? We know that V0 is 0. It's 0, 0, 0. If we plug in 0 here, what do we get? Based on this function, if I plug in 0, what do we get? If I plug in 0 here, C1 stays the same. 3 times 0 squared plus C2 is C2. If I plug in 0 here, 2 times 0 plus C3 is C3. If I plug in 0 into the velocity function, I get C1, C2, C3. Then, by matching the vector here, C1 must be 0. By matching the vector here, C1 must be 0. C2 must be 0. C3 must be 0. So C1 is 0, C2 is 0, C3 is 0. They are all zeros. Then plug in 0. Plug in 0. If we plug in 0, the velocity function can be rewritten as 0, 3t squared, and 2t. If we plug in 0 for C1, C2, C3, velocity function can be rewritten as 0, 3t squared, and 2t. Next, from velocity to displacement, we take another antiderivative. From velocity to displacement, take another antiderivative, which is r of t. Antiderivative of 0 is a constant. Here we use a different constant called d1. Antiderivative of 0 is a constant. Here I use a different variable called d1. Use different letters called d1. Take antiderivative for 3t squared. We have t cubed. And every time when we take antiderivative, add constant. Let's call this constant d2. Then when we take antiderivative for 2t, we get t squared. And when we take antiderivative, add constant called d3. Then we try to plug in 0. We know R0 is 1, 2, 0. So plug in 0 into this function and try to match and find D1, D2, D3. We know R0 is 1, 2, 0. We try to plug in 0 here and try to match these vectors and find D1, D2, D3. If I plug in 0, into the displacement, I have D1. 0 cubed plus D2 is D2. 0 squared plus d3 is d3. Then try to match. R0 is 1, 2, 0. What we have here is d1, d2, d3. By matching the vector here, we can see that d1 is 1, d2 is 2, and d3 is 0. By matching the vector, we can see that d1 is 1, d2 is 2, and d3 is 0. Then plug in. The displacement is r of t. The displacement is r of t equal to 1, comma t cubed plus 2, comma t squared. This is the displacement, which represents the location of an object. This is a displacement, which represents the location of an object. Here, in the problem, we're looking for the location of an object when t is 3. So we plug in 3 into this vector function. Plug in 3 into this vector function. If I plug in 3, I get 1. 3 cubed is 27. 27 plus 2 is 29. 3 squared is 9. So, since we treat this as a position vector, the location is a point. The location of an object is 1, 29, and 9. The location is a point, 1, 29, and 9. We treat this vector as a position vector. Treat this as a position vector. Treat this as a position vector, right as a point, 1, 29, and 9. Next example, a baseball is hit 3 feet above ground level with a speed of 100 feet per second and an angle of 30 degrees with respect to the ground. Part A, find the maximum height the baseball can reach. Part B, find the horizontal displacement when the ball hits the ground. Part C, Find the speed when the ball hits the ground. Part D. If there is a 10-foot fence 300 feet from the home plate, will the baseball go over the fence? So, a baseball is hit 3 feet above the ground with a speed of 100 feet per second and an angle of 30 degrees with respect to the ground. A ball is hit in this direction with a speed of 100 feet per second. Then we know the particle, the baseball will eventually go up, reach the maximum height, then go down and hit the ground. The baseball is 3 feet above the ground. Then it's hit with a speed of 100 feet per second with an angle of 30 degrees with respect to the ground. Then when the ball is hit, it will eventually go up. Then since there's gravity will pull object downward. Gravity will keep pulling up the ball downward. Eventually the ball will hit the ground. First question asks the maximum height the baseball can reach. The maximum height that the baseball can reach. That's the first question. Second question, find the horizontal displacement when the ball hits the ground. When the ball hits the ground, what's the horizontal displacement? That's what we are looking for in part B. Part C, find the speed when the ball hits the ground. Find the speed when the ball hits the ground. What's the speed when the ball hits the ground? Part D, if there's a 10-foot fence 300 feet from the home plate, if there's a fence 300 feet away from the home plate, if there's a 10-foot fence 300 feet away from the home plate, it's 10 foot. Will the baseball go over the fence? Will the baseball go over the fence? Will the baseball go over the fence? So this is the questions. First of all, let's write down the given information first, and then try to find the displacement. It's all about the displacement of this object. So write down all given information first, and then try to find out the displacement of this baseball. What do we know? A baseball is hit 3 feet above the ground. That means when time is 0, the initial displacement is 0, 3. Horizontally, there's no displacement. The ball starts here. Horizontally, there's no displacement. So the horizontal displacement is 0. The vertical displacement, the ball is 3 feet above the ground. So the vertical displacement is 3. Initially, the ball is 3 feet above the ground. So that's the vertical displacement. That's the horizontal displacement, and that's the vertical displacement when time is 0. That's called the initial displacement. R0. That's R0. Next. The ball is hit with a speed of 100 feet per second and an angle of 30 degrees with respect to the ground. Let's try to find the decomposition of the speed. Let's try to separate the speed into two pieces. Separate the velocity into two pieces. Let's find the horizontal velocity and the vertical velocity. Let's try to find the horizontal velocity and the vertical velocity. For the horizontal velocity, this side is 100. Refer to this angle, this side is adjacent. So, the horizontal displacement can be written as 100 times cosine 30. This is adjacent side. Refer to adjacent, we need to use cosine. Adjacent over hypotenuse. So, that's the horizontal velocity. That's the initial horizontal velocity. Initial vertical velocity is 100 times sine 30. Because the length of this side is the same as this side. The length of this side is the same as this side. Refer to this angle here. This side is opposite. This is hypotenuse. Opposite of hypotenuse is sine 30. So this is the horizontal displacement, and this is the vertical displacement. Let me show you a bit better picture here. This is the velocity, 100 feet per second. That's an angle 30. This is the horizontal velocity. This is the vertical velocity. We try to find horizontal velocity and the vertical velocity. Let me form a triangle here. Refer to this angle. This is adjacent side. This is hypotenuse. So horizontal velocity cosine 30 is horizontal velocity over 100. If we try to solve for horizontal velocity is 100 times cosine 30 degree. That's the initial horizontal velocity. This is the initial horizontal velocity. Then for initial vertical velocity, this side is the same as this side. Refer to this angle. This is opposite. This is hypotenuse. So we know that sine 30 is the vertical velocity divided by 100. Then if we solve the equation for vertical velocity, the vertical velocity is 100 times sine 30. Those are the initial horizontal and vertical velocity. So initial velocity is initial horizontal velocity is 100 times sine 30. Initial vertical velocity is 100 times, this is cosine. Initial horizontal velocity is 100 times cosine 30. Initial vertical velocity is 100 times sine 30. That's the initial horizontal velocity. That's the initial vertical velocity. We find a decomposition for this speed and angle. Based on the decomposition, we find the horizontal velocity and the vertical velocity. Then if I simplify, this can be rewritten as cosine 30 is radical 3 over 2. So I get 50 radical 3. Sine 30 is half. 100 times half is 50. That's the initial velocity. What else do we know? We know the acceleration function. We know near the Earth, gravity is always pulling object downward. Near the Earth, gravity keeps pulling object downward. So horizontally, vertically, there's a force keep pulling object downward, which generates an acceleration of negative 32 feet per second square. G is about 9.8 meter per second square, or negative 32 feet per second square. That's an acceleration generated by the gravity. Near the Earth, since there's gravity added to the forces, it generates a velocity. So it generates acceleration, 9.8 meter per second square, or 32 feet per second square. Since in this problem, the unit is feet, so we use 32 feet per second square. And since gravity is pulling object downward, we use negative 32 as the vertical acceleration. So that's the vertical acceleration. Horizontally, there's no forces keep added to the object. Horizontally, there's no forces keep added to this baseball. So the horizontal acceleration is 0. Here the vertical displacement is, the vertical acceleration is negative 32 feet per second squared. Horizontal acceleration is 0. Then, based on the given information here, we try to find the displacement of this baseball. Based on this given information, we try to find the displacement of the baseball. Let's find the velocity first. We need to find the displacement of the baseball, r of t. Let's find the velocity first. Take antiderivative twice, find the velocity. From acceleration to displacement, we must take antiderivative twice. So let's take antiderivative. If I take antiderivative for acceleration, I get a velocity. Antiderivative of 0 is a constant. That's why C1 here. Antiderivative of negative 32 is negative 32t. But every time when we take antiderivative, add constant called C2. Then we know the initial velocity. Since we know the initial velocity, we can plug in 0. If I plug in 0 here, what do we get? If I plug in 0 here, I get C1, comma C2. Then by matching V of 0 here, by matching the initial velocity here, we can see that here, C1 is 50 radical 3, C2 is 50. By matching the initial velocity here, we can see that C1 is 50 radical 3, C2 is 50. By matching, we find C1, C2. Then plugging C1, C2, we find a velocity function. Plugging C1 and C2, we find a velocity function. So the velocity is 50 radical 3 and 50 radical 3 and negative 32 plus 50. Negative 32t plus 50. Next, based on the velocity, we try to find the displacement. So take another antiderivative. We try to find the displacement. For r of t, take another antiderivative. When we take antiderivative, 50 radical 3, that's a constant. When I take antiderivative, multiply by t. And every time when we take antiderivative, add constant. Here, let me use d1 as a constant. Then for the second component, take antiderivative, I get negative 16t squared plus 15t. And when we take antiderivative, add constant called d2. That's the displacement. That's the displacement vector. Next, we know that R0, initial displacement is 0, 3. We need to plug in 0 and try to match d1 and d2. Plug in 0, try to match d1 and d2. If I plug in 0 into the displacement, we can see that 50 radical 3t. If I plug in 0 for t, that's 0. So I get d1 here. If I plug in 0 for t, I get d2. Then by matching here, we can see that d1 is 0, d2 is 3. Then we plug in 0 for d1, plug in 3 for d2. So here I plug in d1 is 0, d2 is 3. The displacement is 50 radical 3t plus 0, negative 16t squared plus 50t. plus d2. d2 is 3. That's the displacement. Now, answer the question. Answer the question. Based on this information, answer the question. First question. Find the maximum height the baseball can reach. Find the maximum height that the baseball can reach. We know that when the baseball reaches the maximum height, its vertical velocity must be 0. When a baseball reaches the maximum height, its vertical velocity must be 0. That means it's not moving upward. Its vertical velocity must be 0. So, in order to find the maximum height for part A, we set the vertical velocity equal to 0. Set the vertical velocity equal to 0. Set the vertical velocity equal to 0. The vertical velocity, this is the velocity function. The first component is called horizontal velocity. Second component is called vertical velocity. So we set negative 32t plus 50 equal to 0. Solve for t. T is 50 over 32, which can be rewrite as 25 over 16. That means at this moment, when t equal to 25 over 16, at this moment, the baseball reached the maximum height. When t equal to 25 over 16, the baseball reached the maximum height. So in order to find out the maximum height, we plug in t into the vertical displacement function. Plugging t into the vertical displacement function. So when t equal to 25 over 16, the vertical displacement is negative 16t plus 50t plus 3. Negative 16t squared plus 50t plus 3. The vertical displacement equal to negative 16 times 25 over 16 squared plus 50 times 25 over 16 plus 3. Then here I use my calculator. I get 42.0625. It's about 42 feet. That's the maximum height that a baseball can reach. It's about 42 feet. It's about 42 feet above the ground. So for part A, set the velocity equal to 0. Set the vertical velocity equal to 0. Solve for t to find out how long does it take for the ball to reach the maximum height. Then plugging t into the vertical displacement, we find the maximum height that the ball can reach. This expression is the vertical displacement. This expression is called vertical displacement. Part B. Part B. Find the horizontal displacement when the ball hits the ground. When the ball hits the ground, its vertical displacement must be 0. When the ball hits the ground, its vertical displacement must be 0. So for B, we set the vertical displacement equal to 0. Set the vertical displacement equal to 0, which means this equal to 0. Negative 16t squared plus 50t plus 3. Set the vertical displacement equal to 0. We try to find out how long does it take the ball to reach the ground. we try to find out how long does it take the ball to reach the ground. So set equal to 0. Then solve this equation for t. Solve this equation for t. Here we can use quadratic formula. We can use quadratic formula here. T equal to negative 50 plus minus square root of 50 squared minus 4 times negative 16 times 3 over 2 times negative 16. Here I use my calculator, I get two solutions. T equal to negative 0.06 and t equal to 3.18. In general, we don't consider negative time. Time cannot be negative. We don't consider negative answers for time. So this answer is rejected. Time is always positive. That means it takes 3.18 seconds for the ball to reach the ground. It takes 3.18 seconds for the ball to reach the ground. And we are looking for the horizontal displacement. We plug in t equal to 3.18 into the horizontal displacement here. So when t equal to 3.18, the horizontal displacement (50 radical 3 times t). This is the horizontal displacement. Equal to 50 radical 3 times 3.18. Here I use my calculator, I get 275.73 feet. So when the ball reaches the ground, the horizontal displacement is about 275.73 feet. Part C. Find the speed when the ball hits the ground. When the ball hits the ground, that means the vertical displacement must be 0. If we set the vertical displacement equal to 0, we get t equal to 3.18. That means it takes this much time for the ball to reach the ground. When the ball reaches the ground, we try to find the speed. We know that the speed is the magnitude of the velocity. And the velocity function here is 50 radical 3 and negative 32t plus 50. Take magnitude. 50 radical 3 square plus negative 32t plus 50 square. Then we plug in t. T is 3.18. That's the time. That's the moment when the ball reaches the ground. We're looking for the speed when the ball reaches the ground. So plug in this t value here. Find the speed when the ball reaches the ground. Here I have 50 radical 3 square plus negative 32 times 3.18 plus 50 square. And here I use my calculator. I got 100.96 feet per second. That's the speed when the ball reaches the ground. That's the speed when the ball hits the ground. Now part D. Part D. If there's a 10-foot fence 300 feet from the home plate, will the baseball go over the fence? If there's a 10-foot fence 300 feet from the home plate, will the baseball go over the fence? So we try to find the height for part D. We try to find the height of the ball when it's 300 feet away. We try to find the height of the baseball when the horizontal displacement is 300. We try to find the height of the ball when the horizontal displacement is 300. If the height is above 10 feet, if the height is above 10 feet, then the ball will go over the fence. But if the height is below 10 feet, if the height is negative or below 10 feet, that means the range is too short. The ball won't reach the fence. So first of all, we set horizontal displacement equal to 300. Set the horizontal displacement equal to 300. Find T. Find out how long does it take the ball to reach 300 feet. Then, at this moment, we try to find the vertical displacement, the height of the ball. If the vertical displacement is above 10, then the ball will go over the fence. If the vertical displacement is below 10 or is negative, that means the range is too short. The ball won't reach the fence, or the ball hits the fence. So for part D, we first of all set the horizontal displacement equal to 300. Set the horizontal displacement equal to 300. That means 50 radical 3t equal to 300. Then solve the equation for t and try to find out how long does it take the ball to reach the fence. How long does it take the ball to reach the fence? If I divide both sides by 50 radical 3, t is 2 radical 3. That means it takes this much time for the ball to reach the fence. It takes this much time for the ball to reach the fence. Next, we try to find out the vertical displacement, the height of the ball when the ball reaches the fence. Next, we try to find out the vertical displacement, the height of the ball when the ball reaches the fence. Now, when t equal to 2 radical 3, the vertical displacement is negative 16 t squared plus 50t plus 3. This is the vertical displacement. Plug in, I get negative 16 times 2 radical 3 squared plus 50 times 2 radical 3 plus 3. Then here I use my calculator. I get negative 15.8. I get negative 15.8. That means the range of the ball is too short. It won't reach the fence. If the height is negative, that means the range of the ball is too short. It won't reach the fence. If the height is between 0 and 10, then the ball hits the fence. If the height is above 10, the ball go over the fence. Since the height is less than 0, the range is too short. The ball won't reach the fence. The ball won't reach the fence. and it won't go over the fence.